Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. A little bit about me. Since 2008, I've worked as a contract administrator for a mechanical engineering firm in the construction industry. What does that mean exactly? Well, I visit construction sites of various buildings throughout construction to ensure the plumbing, HVAC, and fire protection systems are installed as per design and applicable codes. I also work with contractors and other consultants to resolve conflicts and answer questions related to the mechanical design. It's a fairly stressful job at times, but I do really love it. As I've said before, starting a podcast has been a dream of mine for a long time. It's been a steep learning curve, which I had somewhat expected. And while I'm happy with the content to date, the delivery isn't quite what I had in mind. I underestimated how nervous I would get when recording. I have all these thoughts and ideas in my head, but when I hit the record button, I start to stumble over my words. I also talk really fast when I get excited, which is sometimes hard to understand. So the episodes to date have been more scripted and monotone than I had intended, but I'm working on it, so please bear with me. I also wanted to talk about why I started this podcast in the first place. I was reading an engineering ethics textbook over the summer. Don't worry, I was studying for an exam. I don't generally read textbooks for fun, although I'm not opposed if it's interesting. Anyways, I found myself drawn to all of the failure case studies in each chapter, but I also realized that there's a lack of engineering failure content taught to young engineers. There's a lot of talk about what to do and what not to do, but how do you prevent failures and what happens when something goes wrong? My hope for this podcast is to help prevent future failures and show that shedding light on problems with the design before the failure occurs is way, way better than waiting for the failure to happen. In the case of the City Court building in episode 1, the engineer was actually hailed a hero for admitting to the design problems and helping to correct them before anything bad happened. I have an exciting episode for you today, the Ford Pinto, which exploded when rear-ended. But first, the news. This week in engineering news, engineers combine light and sound to see underwater. Today, most underwater mapping is done by attaching sonar systems to ships. This technique is very slow and very expensive. Sound or light waves cannot pass from one medium to another, in this case from air to water, or vice versa, without losing most of their energy. So in a mapping scenario from above the water surface, the wave would pass from air to water and back again, which ends up doubling the energy loss. The Photoacoustic Airborne Sonar System, or PASS, was developed by researchers at Stanford School of Engineering this year. PASS uses light in the air and sound in the water, where both travel well. They fire a laser from the air to the water surface, which generates ultrasound waves when it hits the water. When the ultrasound waves reverberate back to the water surface, it still loses some energy, but it's not double like it would be using traditional methods. To date, the PASS system has only been tested in a lab in a container about the size of a fish tank, but the researchers are optimistic that the concept can be transferred to open water settings. Did you guys hear or read about the One Opus container ship that lost almost 2,000 containers in early December? The ship hit a storm about 3,000 kilometers northwest of Hawaii as it was traveling from China to California. Because the containers are filled with air, they float just below the surface for a while before sinking, making them super dangerous for other ships to run into. The PASS system is something that would be very helpful to not only retrieve the containers, but also warn other ships of their location. It could also be used to help find airplanes, like the Malaysia Airlines Flight 370 that went missing mid-flight in 2014, which is a really sad story. There are so many applications for this system. Please check out the link in the show notes if you want to read more on the Photoacoustic Airborne Sonar System. Now on to this week's engineering failure, the Ford Pinto, the car that exploded when rear-ended. In order to accurately discuss the Pinto, we have to hop in our Wayback Machine to the middle of the 20th century. It was a much, much different time. Until the 1960s, automotive safety was not at the forefront of design, manufacturing, or even sales, which is crazy because safety is one of the biggest factors buyers look at today when purchasing a car. But in the 60s, it was believed that accidents were caused by bad drivers and poor roads, not unsafe cars. Cars were not expected to survive accidents. They were designed for normal use but not crashworthiness, even though 1/3 to 3/4 of all automobiles are involved in accidents. One common argument from the automotive industry was that manufacturers know cars can be driven into a body of water, but that doesn't mean they need to be equipped with flotation devices. I laughed when I read this the first time. It's a bit ridiculous and short-sighted. Lower safety levels were more acceptable for smaller, cheaper cars than they were for larger and more expensive ones. Safety devices were offered as optional, and small vehicle vulnerability was assumed to be an intrinsic part of their nature. Triumph Motors argued in 1974 that preventing fuel tank fires would, quote, discriminate against small vehicles. In 1956, Ford sold a safety package with their cars. Sales were initially strong but dropped off, and Ford ended up canceling the campaign ads halfway through the year. Safety doesn't sell became the motto of the automotive industry. They also sold this idea to President Nixon in 1971. In the 1960s, Lee Iacocca, known as the father of the Mustang, urged Ford management to pursue compact car design for fear that German and Japanese manufacturers would capture the subcompact market. To get the car in the showroom with the 1971 lineup, the conception to production schedule, which is normally 43 months, was shortened to 38 months. Design started in 1967. Tooling takes 18 months, so it began shortly after design, and production began on August 10, 1970. The motto of the Pinto design, as stated by Iacocca, was, quote, the Pinto was not to weigh an ounce over 2,000 pounds, or 900 kilograms, and not cost a cent over $2,000. $2,000 is equivalent to roughly $12,800 today. The Pinto would still be heavier and costlier than other cars in the very competitive compact car market, but it still did okay. Due to styling and aesthetic constraints, locating the gas tank over the rear axle, a location known to prevent fire and rear-end collisions, was not desirable. To increase the luggage department or trunk, the gas tank was relocated to the car's rear, right in front of the bumper. This resulted in the gas tank being outside the frame of the car. The car was released for sale on September 11, 1970 for $1,919, which is competitive with the Beetle and Chevy Vega at the time. The 41-liter tank was sheet metal and attached with 2 metal straps. The fuel pipe was attached to the inner side of the driver's side rear quarter panel with a bracket. The other end slid through the top left side of the tank through a sealed opening. In an accident, the fuel fill pipe was dislodged or the tank itself was punctured or torn. This resulted in fuel leaking onto the ground or into the passenger compartment and often led to a fire. Since the 1980s, designers have located fuel tanks within the vehicle frame outside the crumple zones of the car, typically ahead of the rear axle. But that was not the case in the 70s. Back in 1966, the Motor Vehicle Safety Act was passed, which allowed the U.S. federal government to put safety standards in place for motor vehicles. This was following 5 years of significant increase in vehicle-related deaths. If possibility of injury is foreseeable, car makers could now be held liable for selling a reasonably dangerous product, and crashworthiness now had to be considered. My dad has a 1952 Oldsmobile, which he calls Ingrid. It doesn't have any seatbelts. The first time I rode in it, I was very confused. I thought the seatbelts were stuck in the seat. I think this was the first time I realized they used to make cars without seatbelts, which now seems insane, but at the time it was the norm. Lap belts were not mandatory in the US until 1968. And then there was Standard 301, which governed fuel safety integrity issues. It proposed an expansion to cover integrity during rear-end collisions. The standard initially covered front-end collisions only when implemented in 1967. A revision in 1969 proposed to expand the standard to cover rear-end collisions. The test conditions were as followed. An 1,800 kilogram barrier was towed at 32 kilometers per hour, colliding with a stationary car. Ford ran the test on cars modified to the Pinto design, because the Pintos were still in production, and implemented modifications into the first Pintos manufactured. Then, in August 1970, the test parameters changed. The barrier was now fixed, and the car was towed backwards into it at 32 kilometers per hour, with a long-term goal of expanding the test to 48 kilometers per hour and adding a standard for vehicle rollovers, which was proposed in August 1973. Ford argued that fire was a minor problem, rear-end accidents were rare, and kinetic force, not burns, caused injury and death for rear-end accidents. Even though independent research found that 400,000 autos were burning each year, causing 3,000 deaths. Rear-end accidents were 7.5 times more likely to result in fuel spills, and the occupants would have walked away unharmed, no cuts, no bruises, no broken bones. Ford stalled the passage of Standard 301 for 8 years. By the time it was implemented in 1976, over 2 million Pintos were manufactured. By 1977, the Pinto had a protected fuel tank. On May 28, 1972, Lily Gray was driving her 1972 Pinto on a California freeway. The car stalled and coasted to a halt in the middle lane. It was hit from behind, and the gas tank ruptured and leaked, causing fire and engulfing the car in flames. Lily Gray died in hospital. Her 13-year-old passenger, neighbor Richard Grimshaw, suffered horrible burns, requiring over 90 surgeries and leaving him permanently disfigured. Their family sued Ford in a highly publicized court case. In February 1978, Grimshaw was awarded $2,516,000 in compensation and $125 million in punitive damages, later reduced to $3.5 million. The case was appealed by Ford, but the ruling stood. The court stated, Ford decided to defer correction of the Pinto's shortcomings by engaging in a cost-benefit analysis balancing human lives and limbs against corporate profits. Ford's institutional mentality was shown to be one of callous indifference to public safety. There was substantial evidence that Ford's conduct constituted conscious disregard of the probability of injury to members of the consuming public. The conduct of Ford's management as reprehensible in the extreme. It exhibited a conscious and callous disregard of public safety in order to maximize corporate profits. There were 2 key witnesses for the prosecution in this trial. Brian Block was a private consultant and very vocal on shortfalls of auto safety. He had testified on other fuel system fault lawsuits. And then Harley Kopp, a previous Ford employee. Supporters believed he was forced to retire because he pushed too hard for auto safety. And then on August 10, 1978, 3 teenage girls died in a fire caused by their 73 Pinto being rear-ended by a van. They had stopped to pick up the gas cap, but there was no breakdown lane, so they stopped in traffic. They were hit by a van going 80 kilometers per hour. The driver was looking for a cigarette he had dropped. The doors were jammed shut from the crash, and the occupants were trapped inside. 2 of the girls died instantly, and the driver died in hospital. A grand jury indicted Ford on charges of reckless homicide and criminal recklessness, the first time a corporation was tried for criminal behavior. In order to prevent legal precedent, Ford assembled a defense at trial, convincing the jury that the Pinto was stopped when it was hit. Therefore, no low-speed collision occurred, and the deaths were not reckless homicide. Brian Block and Harley Kopp testified in this trial as well. Harold McDonald, an engineer in charge of Pinto's design, testified on behalf of Ford. McDonald's father had died in a fire when his Model A burst into flames after a front-end collision with a tree. The Model A's gas tank was in front of the vehicle, close to the driver. McDonald felt very strongly that the gas tank should be as far away from the passenger compartment as possible. He thought that placing the gas tank above the rear axle was closer to the passenger compartment and more likely to be punctured by items in the trunk. Placing the tank above or straddling the axle would be more vulnerable to side impacts, which were over twice as common as rear-end collisions. Placing the tank above the axle would raise center of gravity, affecting handling properties. Increasing the length and angle of the fuel fill pipe would make it more susceptible to damage. And relocating the fuel tank would reduce trunk capacity, make servicing more difficult, and a station wagon or hatchback model would not have been possible. Almost all American-made cars at the time had a tank behind the rear axle, not just the Pinto. This represented acceptable engineering practice at the time. Ford was not found guilty of failure to warn, but their reputation was harmed forever. The National Highway and Traffic Safety Administration investigated the Pinto's safety in 1977 and issued their report in May 1978. As part of their investigation, rather than a flat-moving barrier, a 1971 Impala would crash into the stationary test car's rear end to simulate real-life conditions. The Impala's front end was loaded with weights, and the headlights of the Impala and taillights of the stationary car were left on. Both engines were running, and both gas tanks were full. 11 crash tests of 1971 to 1976 model Pintos were tested with speeds between 48 kilometers per hour and 56 kilometers per hour. Of the 4 vehicles tested at 56 kilometers per hour, 2 caught fire and 2 leaked fuel. Chevy Vegas were also tested as a control car in this investigation. They leaked smaller amounts than the Pinto at all speeds, but they didn't catch fire. Ford argued that the test was unfair because all subcompacts had similar risks, although maybe not to the same extent as the Pinto. Everyone else seemed to be able to deflect criticism, except Ford. The investigation found that rear-end collisions of Pintos can result in puncture and other damage to the fuel tank and fuel fill pipe, causing substantial fuel leakage. When rear-ended by a full-size vehicle, the fire threshold is 48 to 56 kilometers per hour, which is residential neighborhood speeds, not very fast. In 1972, the National Highway Traffic Safety Administration had set a cost of $200,725 per human life. Numerical values had to be placed on human life in order to provide this data. Based on a cost of $11 per car to strengthen the gas tank integrity, Ford did a cost-benefit analysis and determined it was not feasible to make the repair. They estimated $49.5 million lost due to burn death, burn injury, and burn vehicles versus $137 million to repair the 11 million cars and 1.5 million light trucks on the road. But 1 month after the 1978 report was issued, under immense public and federal government pressure, Ford initiated a recall to replace the filler pipe and add 2 polyethylene shields to protect the tank. The recall was estimated at $20 million after taxes, which is 20% of the cost of death and burn-related costs, and 14% of the initial recall estimate. That being said, it was the largest automotive recall campaign at the time. Formulating rationale of company profit had become a way for engineering teams to communicate effectively with non-engineers in the company, although engineers amongst themselves understood acceptable risk. But you have to find a way to help non-technical people understand how and why certain decisions are made on the engineering side. Many modifications exist, but implementing them all is cost prohibitive. A cost-benefit analysis is a widely acceptable selection method, although I wish that corporations would be more responsible in designing safer products. Despite Ford's outward stance that the Pinto design was fine, they were aware of the dangers. Ford had done some testing of their own and was aware of the fire risks as early as 1968, and that a relatively inexpensive solution was available. Ford partially financed a UCLA study that recommended the gas tank be placed above the axle and not adjacent to the rear bumper. In 1969, 3 Ford engineers modified Ford Capris to move the gas tank to the rear. They backed the vehicles into a wall at 28 kilometers per hour. The welds on the gas tank split open. The tank was damaged when it hit the axle. The fuel fill pipe was pulled out, and the tank fell out of the car. The gas spilled into the interior of the car when the welds split open. They also ran the same test and rear-ended the vehicle at 33 kilometers per hour. Gas leaked from the fuel pipe or from the punctured tank. In a 1970 test, a Pinto was backed into a wall at 33 kilometers per hour. The rear end was crushed 18 inches. The fuel fill pipe was pulled out of the tank, causing spillage. There was a puncture in the upper right front surface of the tank caused by contact between the tank and a bolt on the housing, and the tank was punctured twice by nearby metal objects. Also, both passenger doors jammed shut, preventing escape and rescue. There were several ideas looked at by Ford to improve the fuel tank issues, such as adding a heavy bladder lining the tank, reinforcing the tank walls, shielding of the tank, additional brackets to keep the tank in place, and a flexible fuel fill pipe. The cost of these changes ranged from 22 cents per car to $6 per car, but none of them were implemented until the recall. Information from these tests and crash test results were pushed all the way up the chain of command, and still no changes were made. Changes required sign-off from several levels of management before they could be implemented. The tests were not seen as sufficiently convincing at the time. Ford thought similar tests with competitors' vehicles yielded similar or worse results, and Iacocca's perceived inapproachability and self-censorship due to a perceived lack of power to change the design or initiate a recall allowed several concerns to go unnoted. One really big blow to Ford's reputation was the Pinto memo, which was published in a Mother Jones magazine article in 1977. The article accused Ford of knowingly causing hundreds of burn deaths while they were unwilling to pay $11 more per car to make the gas tank safer. But here are some important things to know about the memo. It was written by Ford employees Ernest Grush and Carol Somdy. It was unknown to Ford employees responsible for technical design and safety decisions. It was intended to influence the National Highway Traffic Safety Administration regulators. It was not intended to be circulated internally at Ford. It was not provided to Ford design engineers or recall personnel. It was written in 1973, and the Pinto was designed in 1967 to 1970, so it couldn't have impacted the design. And it was written in relation to rollover accidents as a cost-benefit analysis associated with design changes. It didn't deal with or mention the Pinto. The final lines of the memo even say, the analysis discussed above concerns only rollover consequences and costs. Similar analysis for other impact modes would be expected to yield comparable results, with the implementation costs far outweighing the expected benefits. It was related to new cars and not just Fords. At the time, there were 12.5 million vehicles sold annually in the United States. Reviews of the Pinto in 96 and 97 came to the following conclusions. Ford engineers didn't consider they were taking calculated risks with consumer lives. They didn't worry about lawsuits when designing, and they did not refuse to correct perceived problems because settling lawsuits would be cheaper. This simply came down to a preference of the W know and the W don't. There were too many unknowns with the new design. Between windshield retention, fuel leakage on front impact, a lack of safety glass, and fuel tank placement, there was a lack of consensus that the Pinto was unsafe. Meaning, yes, the tank was unsafe, but also all this other stuff is unsafe. It seems like everyone just assumed compact cars were less safe at the time. There was a really interesting comparison of 1975 and 76 all-cause fatalities per million vehicles. Rear-end collisions made up about 15% of the accidents. The Pinto ranked fourth in least fatalities out of the 8 vehicles reviewed and better than average. The Datsun 1200 or 210 was the worst in both years. The National Highway Traffic Safety Administration finding found that 38 collisions for Pintos resulting in tank leakage or fire resulted in 27 deaths, which coincidentally is the same number allegedly caused by Pinto transmission problems, a problem that was relatively unheard of, and there was definitely no recall issued for the transmissions. When I started researching this episode, I was expecting to find a number of flaws with the Pinto design, as well as a conspiracy of bureaucratic and capitalist cover-ups, but that wasn't quite what I found. There was no conspiracy. Things just happen in a normal way that a technocratic bureaucracy proceeds. It seems like everyone's compact cars had one safety issue or another, and that while several Pinto accidents resulted in death, the Pinto was not the deadliest vehicle on the road. I've got to say my thoughts on the Pinto have changed. The former National Highway Traffic Safety Administration head Douglas Toms even said that the Pinto was a conventional automobile and was designed and constructed comparably with most other cars of its type at the time. Check out the podcast page, link in show notes for photos from this week's episode. And if you want to chat with me, my Twitter handle is @failureology. Thanks everyone for listening, and if you're enjoying what you're hearing, please rate, review, and subscribe to the podcast so more people can find it. And don't forget to tune in next week to hear about the Quebec Bridge, the bridge that collapsed twice. But more on that next week. Bye everyone. Talk soon.